All right, here we go with section 5.1 on the natural log function, and we are dealing with differentiation today, only doing derivatives of the natural log function. In the future, we will be doing integrals, but we're just starting today with the derivative. So the natural log function for calculus is defined as ln x equals the integral from 1 to x of 1 over t dt. So that gives you a little bit of insight into possibly what the derivative might look like. We are more used to seeing the natural log function in relation to exponentials, and that natural log is the inverse of the e to the x function. That's what we've used it for in the past. So let's just go back to what we know about the logarithmic properties of natural log, in that everything we've learned in Algebra 2 and in pre-calculus, these are all the properties they should be absolutely review. If we have natural log of 1, it's 0. Natural log of a product can be split into two separate logs that are added together. Natural log of a to the n, that exponent comes down to the front as a coefficient. And the last one, natural log of a quotient, turns into two terms, natural logs, as a difference. So let's first go ahead and use all of those properties before we start calculus to make sure that we remember, because we will be having to use some of these to make our lives a little bit easier, so we need to make sure we remember how to do everything properly. Letter A is a quotient, so we're going to start by splitting that into two natural logs that are subtracted. That's really it. There's nothing else we're going to do there, just using our properties. Letter B, I'm going to first rewrite this. Instead of the square root, we're going to put that as a 1/2 exponent, because one of our properties is that any exponent comes down to the front as a coefficient. Okay, third one, there's a couple steps to do on letter C. I will first split, whenever I see that fraction, I always split with the difference first. So we're going to have natural log of 6x minus natural log of 5, and then we need to further split up the 6x, because that is technically a product of 6 and x, so that's going to be split into two separate logs that are added together. Okay, letter D's got a lot more going on. Um, what is a good starting place? Again, I always start where I see that bar. I think, okay, I'm just going to split it up with subtraction, and then we can work on each individual term after that. So I'm not going to change anything except for splitting up the fraction into two separate subtracted natural log terms. And that is the cubed root. I know it looks like x cubed, but that 3 is above the root, so that is the cubed root of x squared plus 1. Okay, so first exponent, the first half here can come down. The inside of that cannot be simplified further. Second half, natural log x, and is being multiplied by the cubed root of x squared plus 1, so that's going to be split into two separate added terms right away in brackets, because we are subtracting that whole thing, so the bracket actually is important for order of operations to make sure that we follow that. And then the last thing I'm going to do is turn that cubed root into a 1/3 exponent, which we know is going to have to come down to the front of that last term. While I'm at it, I'm going to distribute that negative through the brackets so that we don't have any parentheses in our final answer. There we go. All right, let's do some calculus now, finally. The derivative of the natural log function is very simple. The derivative of natural log is 1 over x, if it's just the natural log of x. But if it's natural log of a function, anything other than x, then you're going to do 1 over u, 1 over the inside, times the derivative of the inside. So a little bit simpler way of stating that would be u prime over u, or the derivative of the inside over the inside, is what I'm going to be referring to it as we go here. So I have to identify my inside. Obviously, it's whatever is in the parentheses. So here the derivative of the inside is 2, and then we do that over the inside. and simplify if we can. Letter B, derivative of the inside is 2x over the inside, x squared plus 1. Letter C, I have a product of x and natural log x, so I need to do the product rule. So we're going to do f times the derivative of g, which is 1 over x, plus g times the derivative of f. So combining x times 1 over x, that is 1, and then just plus the natural log of x. And letter D is involving the chain rule since I have the function being raised to another function. So remember how to do the chain rule. We have to bring down, if there's an exponent like this, we have to bring down the exponent, leave the inside alone, lower the exponent, and multiply by the derivative of the inside, which is 1 over x. I would probably leave it like that. If you felt like simplifying it further, I would just combine the 3 and the 1 over x. But that is not a have-to step. Okay, so sometimes we can use those properties that we talked about earlier, those Algebra 2 pre-calc properties, to simplify a logarithm first so that taking the derivative is not such a pain. So I don't necessarily have to do the chain rule with this. Remember that the square root is the same thing as a 1/2 exponent. I don't have to do the chain rule with that like I did on the previous question. I can just bring down that 1/2 just using logarithm properties. There's no calculus involved yet. And now when I do my derivative, I don't have to worry about the chain rule bringing down the exponent. So that's actually pretty nice. The 1/2 derivative of the inside is 1 over the inside. I would say, I don't think I'd necessarily multiply it in. You can if you feel like it, but I would write it like that. So saved yourself a little bit of stress without having to do the chain rule for that one. For example, I don't really want to do the quotient rule with 2 chain rules involved. I think I would rather try to do some logarithmic properties to split this up into several much simpler logarithm terms so that this is not such a pain in the butt to take the derivative of. So the first, I'm just going to start splitting it up. The top versus the bottom will be split using subtraction. The first half is going to be split again using addition. And I'm going to bring that 2 down right away as well. And then the second half, that 1/2 comes down. Now I don't have a super complicated one logarithmic derivative defined. I have 3 simple logarithmic derivatives defined, which is my preference for sure. Derivative of natural log x is the simple one, 1 over x. Derivative of natural log x squared plus 1, we do the derivative of the inside over the inside. And last one, derivative of the inside over the inside. And I would probably do one more step to simplify a little bit so that there's no numbers on the outside like that. So we have 1 over x plus 4x over x squared plus 1 and minus 3x squared over 2x cubed minus 1. So again, for me, much more preferable to do 3 simple logarithmic derivatives than one overly complicated logarithmic derivative. You would certainly get equivalent answers if you didn't think to do those logarithmic properties right away, but it's more likely in my opinion, that you would make some sort of algebra mistake along the way and get that question wrong versus if you just did the algebra first and split it up into those simpler ones. Okay, so this isn't even a logarithm equation. It says to find the derivative. Could I do this using the quotient rule with the chain rule twice? Yes, absolutely I could, but as we just discovered, I think I'd rather split it up into several terms if possible. Here it's not possible because it's not a logarithm. So there's something called logarithmic differentiation where you take the logarithm of both sides. So that's what we're going to go ahead and do. Take the logarithm, natural log of both sides. And again, as long as you're doing it to both sides, nothing is changing a lot. Wouldn't be able to do it if it changed it. And then, okay, hey, I got logarithms now, so I can do those logarithmic properties on the right side to turn this into some simpler math. So we're going to have 2 natural log x minus 2 minus 1/2 natural log x squared plus 1. Okay, so now I'm going to take the derivative of every term that I see. Keep in mind when I take the derivative of the left side, this is implicit differentiation. So I'm going to have 1 over y dy dx. When I take the derivative of a y term, I have to put that dy dx there to indicate I took the derivative of a y term. Versus on the right side where I just treat it like normal, derivative of the inside over the inside, both pieces. Okay, simplify. I'm just going to put that 2 in, and then same thing, I'm going to put in the 1/2, which is going to cancel with the 2 on top. Oops, that looks terrible. Okay. Now the trick here is I want to get dy dx by itself, right? That's what you do when you implicitly differentiate, is you want to solve for the derivative. If I want to get dy dx by itself, I need to get rid of this y on the left side, which means I'm going to have to multiply both sides by y. I really don't want to leave a y in my answer though, so what is y? I can go back up here. Oh, look, y is this whole mess. So that can be substituted in for this y variable here. And dy dx is equal to, parentheses, brackets, it doesn't matter, our derivative that we found times the original function y, which is x minus 2 squared over the square root of x squared plus 1. If we were to have ignored the fact that this was logarithmic differentiation and we had just done the quotient rule with the chain rule on the top and the bottom, we absolutely would have gotten to the same place. It would have been equivalent anyway. It might not have looked exactly the same. But if the question tells you to use logarithmic differentiation to find the derivative, you absolutely have to take the log of both sides and turn it into a logarithm problem. If it doesn't tell you to do that, I mean, feel free to use either method, whichever one you're more comfortable with. Okay, so here's a little unique one. If we're doing the natural log of the absolute value of u, it looks like my answer is literally exactly the same as if it was just natural log u. So just know that that absolute value is not going to change it. Normally we can't take the derivative of absolute value things, but as long as it's inside of a natural log, you're going to treat it like it's not even there, which is really interesting. You'll see why in the next section. Okay, so we have natural log, absolute value, cosine. So we're still going to do the derivative of the inside, which is negative sine over the inside, which in trigonometry world simplifies to negative tangent. I would expect you to make that substitution. That one's a pretty basic one. All right, last question here is finding relative extrema of this function involving a logarithm. So I'm just going to take the derivative like I would anytime I'm looking for extrema. dy dx equals the derivative of the inside, 2x plus 2, over the inside. Now, when I have a rational equation such as this, to find extrema, I want to know where the derivative is equal to 0. When it's rational, I'm going to set the top equal to 0 and solve it. That's going to give me my critical point. So it's going to give me -1 as my critical point. And then I'm going to do my testing with my intervals and find that at -1, it is a minimum at -1, and then I plug that back in to the original and get natural log 2 for the y value. Okay, our homework is there, and that was section 5.1 on natural log derivatives.